All right. Hi, everyone. My name is Erin, and I'm also joined by Jacob. And today we're going to be doing the AP Physics 1 algebra-based student Q&A session. Some rundown. Okay, for momentum, that unit kind of hits on a lot of different principles that you're probably going to see on the exam. So this year, since it's only 2 FRQs, you're really not going to need to know a lot of the math that's going to go into it. I really doubt they're going to give you math-related momentum, but you can know momentum is P equals mv, mass times velocity. And momentum itself refers to the quantity of motion that an object has, mass and motion, if you've heard that term before. There's also impulse, which is the change in momentum. So for this unit, really, I remember when I took the exam, the main things that I focused on was the conservation of momentum in collisions. So I'm sure you've heard about inelastic and elastic collisions before. Elastic collisions are when two objects hit and they bounce off each other. So kinetic energy is also conserved in a perfectly elastic collision. But an inelastic collision, only momentum is conserved. So you kind of want to know the principle of conservation of momentum and also how momentum pertains to like the center of mass and when it's conserved in those scenarios. And you're also going to want to know about force time graphs. So the area under a force time graph is impulse, or your change in momentum, because impulse is force times time. I don't have much else to add. I would really recommend watching. I know Fiveable has a whole unit overview on momentum, like the study guide that you can go through. But really, you really need to understand the difference between conservation of momentum and conservation of kinetic energies in those collisions, and also just the idea of impulse and momentum themselves.
One thing I want to add to that is a lot of people forget that momentum is a vector. So momentum isn't just conserved in one direction, it's conserved in all directions. So a lot of times you'll have two unknowns in a momentum problem, and people don't know how to solve it because people take the approach of putting one equation in one dimension. Meanwhile, you need to set up both equations in both dimensions, and at that point you have two equations with two unknowns, and that's solvable with just algebra.
Awesome. Thank you so much for that question. We have a second one that is a circuit with two batteries. So from my understanding, DC circuits will not be on the exam this year. It's just units 1 through 7. So you're just going to have to know everything up to torque and rotational motion. It doesn't go past into waves or DC circuits or anything like that. So I don't believe that's anything you're going to see. Do you have anything to add to that?
Uh, yeah, it's exactly right. One problem solving thing, I'm just going to hit it quickly though, because a lot of
Mm-hmm.
people ask these questions like because they're just interested in them, not for the exam. A big point is that like you really do need to identify which is the positive end and the negative end of the battery. So when you're drawing that loop through that battery, if the loop leaves the positive end, then the voltage drop is, or rather, you gain voltage, you don't drop voltage. Khan Academy does have great videos on this kind of stuff. So if you just look up multi-battery circuits, I'm sure you can find great resources for that. But that's not in our slides, so I don't want to focus on it too much.
All right. So if we don't have any other questions, we can get started with, we have 3 FRQs prepared. So we have the 2016 exam question 1. Oh, is this just a physics 1 stream? Oh, this is just a physics 1 stream, but I'm currently taking physics 2, so I can hopefully answer some physics 2 questions, but I know Jacob is really well versed in those topics, so.
Yeah,
Um,
feel free to ask whatever, and we'll answer it. But the thing is, like, you guys are free to answer questions while we're going through the FRQs. It's very clear whether we can ask or answer it in a one liner in the chat, or if we have to take extra screen time, and we're fine to take extra screen time for your questions. So feel free to ask whatever. The chances are, if it's a physics 2 question, we're going to prefer if it's a one liner question because we don't want to spend screen time for something that people aren't studying for.
mhm.
Okay, so we can move on to the first FRQ.
Awesome.
So the first FRQ, what it is it says a wooden wheel of mass m consisting of a rim with spikes rolls down a ramp that makes an angle theta with the horizontal as shown above. The ramp exerts a force of static friction on the wheel, so the wheel rolls without slipping. On the diagram below, draw and label the forces, not the components, that act on the wheel as it rolls down the ramp, which is indicated by the dashed line. To clearly indicate at which point on the wheel each force is exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. The length of the arrows need not indicate the relative magnitudes of the forces. So when you're drawing the free body diagram, there's a lot of things you can mess up here, which is kind of unfortunate because these are sort of seen as the easier points. So the first thing is normal force. Normal force always occurs at the point of contact between two objects, so that's why the arrow starts at the bottom of the wheel relative to the ramp, and it goes directly perpendicular to the ramp, which is why it makes that 90-degree angle with a dashed line. Force of gravity always points down and always acts in the center of mass. People are kind of confused by that because they see that there is mass that is not at the center of mass. Like, why isn't the force of gravity starting at the top of the wheel if there's mass at the top of the wheel? Well, the force of gravity is actually sort of an all-encompassing force that acts on every single little piece of the mass on the wheel, and that ends up being a part of that ends up just being the center.
There's a quick question, in chat.
Yeah, I'm gonna answer that because I don't think if you haven't taken calc, you probably don't know Gauss's law is in the first place. No. Gauss's law is a calc-based thing, so that definitely won't be tested on physics 2. So to continue, the force of friction. So a lot of people's thought process here is the force of friction acts opposite to motion and it's going down the ramp. But in the case of a rotating object, that's actually not necessarily true. If you think of how the wheel is rotating clockwise. And when it's going down the ramp, that's sort of an intuitive thing, I believe. So it's rotating clockwise down the ramp. So there has to be some torque to push it that way because you need torque to angularly accelerate it in that direction. So that torque has to be the force of friction. So that force of friction points in the way that would rotate the wheel clockwise. There are some examples where it's going up the ramp and force of friction is up the ramp. And another thing that's kind of confusing is people always say, well, the force of friction is always opposite to motion, which is true generally. However, it's a force of static friction. Technically, the bottom of that wheel with respect to the ramp is stationary, which is kind of hard to visualize for a lot of people, but it's stationary with respect to the ramp. So the force of friction doesn't really obey the law of it acting opposite of motion. It obeys the law of static friction, or rather the laws of static friction. So you get 1 point for the gravitational force. You get points for labeling your forces. Yeah, actually, if a wheel is going up a ramp, rotating, then it is in the direction of motion. And then you get the normal force with contact, and basically you just get 2 points for your entire free body diagram being right. And they give you one specific point for the force of gravity, and I think that's the easiest one to label.
Definitely. And one thing to add, I remember this FRQ pretty vividly, and looking through the student samples afterwards, I saw one student sample that had every force pointed in the right direction, but it wasn't at the right point of contact. So just to reiterate what Jacob says, it really does matter. This does seem like the easy question, the easy grab FRQ, but it really matters, I'm sure, this year when it's all typed out responses. You might have to describe an FRQ. Super imperative that you guys insert, oh, this force is at this point of contact on the free body diagram to get those points.
Yeah. So next part of the question, it says, as it rolls down the ramp, which force causes a change in the angular velocity of the wheel with respect to the center of mass? So I sort of touched on this, right? So let's look at the 3 forces that are acting on it, all 3 of them, and we can discard 2 of them as causing any torque at all, right? Because for something to change in angular velocity, it needs to cause a torque. So if you look at the force of gravity acts directly at the axis of rotation. And by the formula for torque, which is force times the radius, where the radius is the distance between where the force is applied and the distance or the perpendicular lever arm or whatever it's called to the axis of rotation. And the force of gravity acts at the center, right where the axis of rotation is. So there's 0 distance between them. So gravity can't cause a torque. The next one, the normal force, the angle between the lever arm and the normal force, so basically where the point of contact is and the axis of rotation, the distance between those, or rather the vector between the axis of rotation and the point of contact, is perpendicular, or not perpendicular, it's parallel to the normal force. So by, again, the torque formula, RF sine theta, that sine theta is 0. So The normal force can't cause a torque. The force of friction, however, is directly perpendicular to the lever arm, and sine of 90 is 1. So you have a full torque equals the radius times the force of friction. So the force of friction is the only thing that can cause a change in angular velocity, which is what the answer is. You just get a point for important note. Actually, you don't get the point if you don't explain it. So it says the point is also earned for the causal chain of reasoning about forces. So yeah, basically correctly explaining that friction is the only force that exerts a torque with respect to the wheel center of mass. And you could either just say that that's the force that causes it. I think it's more rigorous in a way to rule out the other forces. Because if you have something that has to be causing a torque, and you have 3 forces, and 2 of them can't cause a torque, then the third one has to cause a torque.
Mm-hmm. And real quick, there was a question asking about the difference between linear quantities like acceleration, velocity, momentum versus rotational quantities. For me, before I'm sure Jacob has a really good explanation for this one, I would really recommend there's a simulator in Peter Apps made like the AP Physics 1 study guide. You can find it on Fiveable. And he linked a simulator where it's like a ladybug spinning on like a little ramp. And that's really, when I was taking Physics 1, that's how I learned the difference between those quantities because it was really hard for me personally to visualize them. I would super recommend going and playing with that ladybug simulator if you're having trouble between those differences. But I'm sure, Jacob, if you have anything to add to that one.
Not really. I mean, the best way to learn something is to actually experience it. Okay, so the next part. For this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite to the force of friction. Derive an expression for the linear acceleration of the wheel center of mass in terms of m, theta, and physical constants. So this is a really wordy one, and for that, I don't really like it that much. But basically, what the point is you have to identify the net forces in the parallel direction of the ramp. And if we look back at the original diagram, we see the force of gravity has a component down the ramp, which I really believe people should have memorized if you're taking this exam. That is mg sine theta. So you have mg sine theta minus force of friction is the acceleration down the ramp. So we'll go back here. So you have to identify that. And then it says for indicating that the frictional force is 0.4 mg sine theta. So where the 0.4 comes from is it says the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite to the force of friction. So we see that the force of friction is some number times the component opposite to it. The component opposite to it is exactly what that parallel component of gravity is. So it's 40% of mg sine theta, which is 0.4 mg sine theta. And then you combine like terms when you solve F equals ma, and you get acceleration is 0.6 g sine theta. I don't really see a question like that being asked where it's really wordy with the percentage, especially with the nature of this exam this year. So if the words kind of confuse you, my tip is just read over it again, and just over it again and again and again until you actually like understand what they're asking you, because I think this is a very vague question. So it says, in the second experiment on the same ramp, a block of ice, also with mass m, is released from rest at the same instant the wheel is released from rest and from the same height. The block slides down the ramp with negligible friction. It says, which object, if either, reaches the bottom of the ramp with the greatest speed? I think it's very, then part 2 says, briefly explain your answer, now reason in terms of energy. I read them both because they're both on the same slide. Answered. So the correct answer is the block of ice, which I think the friction idea is pretty intuitive. The block of ice has less friction, so it goes down the ramp faster. And then it also says in terms of energy conservation. So a block in general isn't going to rotate, which means that all of the gravitational potential energy at the top of the ramp can turn into or translational kinetic energy. Whereas for the rotating wheel, what we have is we have to have some of the gravitational potential energy turning into rotational kinetic energy because it can rotate. So what we have here is we have the block having overall more translational kinetic energy than the wheel. And because translational kinetic energy is proportional to the square of the speed, it has a greater speed going down the ramp. So a question could be asked with it being a block of the exact same material, which means it would have the exact same friction force as the wheel. And in this case, you have to pretty much turn to the energy argument, but they were a little generous here with making it ice. And that's the end of the first FRQ we're going to go over.
Awesome. There was a question from Just COVID the Flu about differentiating between positive and negative work / internal energy, heat flow. She always mixes up the signs. Any tips?
You go ahead and go over the FRQ, the next one on the next slide, and I'll try and answer that.
Okay, awesome. Okay. Could you advance the slides? Awesome. All right, so this is the AP Physics 1 FRQ from the 2019 exam. This is question 1, part A. And so this is going to be a more torque and rotational motion focused question. So the first thing that it's asking us is about the center of mass. So it's basically, the question is telling us a description of what the plunger is doing to block 1. So from time TA to TB, the plunger is in contact with the block and it's moving at a constant force. And then from time B to C, the block loses contact with the plunger, so it's just going on ahead. And then C and D, it encounters a surface with friction. And then from at point E, the two blocks collide and continue moving past point F. So this part A, is asking us to do a graph of the speed of center of mass. And it's really important to pay attention about what it's asking, because I know from reading the chief reader's report for this part of the exam that a lot of people were mistakenly graphing the speed of block 1. So you really have to pay attention to those units on the graph. So the first thing I would do when approaching this is just break it down into sections. So it tells us from time A to time B that it's going to be, constant net force. There's going to be that external net force from the plunger that's causing motion. So we're going to have a constant acceleration. So since it's a speed, which is the magnitude of velocity, it's going to be a constant, upward slope indicating that velocity is increasing, or the magnitude component of the velocity is increasing. So then from B to C, we know that the plunger loses contact with the block. So it no longer has that net external force. It no longer has that acceleration. Because remember, when a net external force is present, acceleration is present. When that net external force is gone, it's going to be moving with constant speed. So that's going to be a flat line for B to C. So then from C to D, we know that it has contact with the frictional surface. So the frictional surface, as shown in the diagram, is going to decrease our speed, or our magnitude component of velocity of the center of mass. So this is the tricky part. If you could go back to the the scoring guidelines. So a lot of people, from the point of where the two blocks collided, a lot of people would decrease the speed and say that, during a collision, the speed's decreasing because it was an inelastic collision and you lose that kinetic energy. So it's inferred that you lose that speed. Well, the problem is this is the speed of center of mass problem. So the speed of the center of mass of a system, actually, since that collision is an internal change, it's not going to affect the speed of the center of mass. We need some sort of external force in order to decrease. So it's going to be at a constant speed, even from after, it exits that frictional force, because that frictional force is a net external force. But once it exits that, there's no net external force acting on the system, since it is a block-block system. So it's going to continue going straight along. So as we can see from the scoring guidelines, you get a point for the straight line indicating the net force for the acceleration segment. You get a flat horizontal point for indicating that velocity, or speed rather, is non-zero, but it's also not accelerating. And then decreases for the friction component, and then you're just going to have constant speed of the center of mass from D to F. So if you have anything to add, Jacob.
No, you hit everything.
Awesome. So for part B, now the plunger is returned to its original position and our blocks are both removed. So we have a uniform solid sphere that's placed at point A as shown. and the sphere is going to be pushed by the plunger from point A to point B, kind of going through the same thing. So, in which intervals, if any, does the sphere's angular momentum about its center of mass change? Check all that apply. So in this situation, if you have kind of a quick overview of what momentum is and how it can be affected, you know that there needs to be a net external torque in order for momentum to change. And the only thing that looks like a net external torque on this problem is our point from C to D. So, you have to not only check point C to D, but we also have to state why it's going to be changing. You have to briefly explain your reasoning to get that second point. Yes. So we have to reason that not only angular momentum is caused by a net external torque, but also that friction is the only force producing an external torque over the entire interval. So that is the 2019 FRQ. Is there a part C or?
I believe so. No, there isn't. Okay, we're going to stay
There
on this part. So someone asked, why does the plunger provide an external torque? I kind of answered it. But basically, the force from the plunger is directly to the right, which is trying to think of how to really answer this. So when you think of the vector from the center of the sphere, which is the axis of rotation, to the surface of the sphere, it points directly to the left. Meanwhile, the plunger force on the ball points directly to the right. So there's no external torque. So what you might be thinking, well, because they're parallel, but you might be thinking, so why does friction cause it? Because it's also in the same direction as the plunger force, or sort of. That's true, but at that point of contact with the surface from C to D, the lever arm is actually pointing directly down, because the vector from the axis of rotation on the ball to the floor is pointing directly downwards.
Mm-hmm.
Does that make sense?
Hopefully.
Yeah.
And just one thing to add, I know when the chief AP reader was discussing this problem, I tried to stay well versed on this FRQ to hopefully clear up some misconceptions, but there was a really common misconception that year that an external force directed at the center of an object produces torque. It doesn't. It needs to be tangentially on the edge of the object. I'm reading hopefully exactly from that chief AP reader exam kind of overview. And I'd really recommend, if you guys are ever, in trouble with any of these FRQs, just do a quick Google, check if the AP reader, the chief reader, has done one of those overviews, because I know when I was studying these FRQs, that really helped, because a lot of students struggle with the same stuff. So yeah, definitely torque is a big one.
Good. Next question. So the next one says, two blocks are connected by a string of negligible mass that passes over massless pulleys that turn with negligible friction, as shown in the picture above. The mass M2 of block 2 is greater than the mass M1 of block 1. The blocks are released from rest. It says the dots below represent the two blocks. Draw a free body diagram showing and labeling the forces, not components, exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitude of all forces. So there's a bit of a weird distinction here, right? So the first one we went over with the free body diagram explicitly said you don't have to worry about the relative lengths, but this one does. So if your relative lengths are wrong, you're wrong. So tension forces are both equal because the pulleys are massless. That's sort of a principle you kind of have to memorize, because the derivation of that is very math heavy and kind of beyond the scope of this class. But it explicitly tells you that M2 is greater than M1. So that force of gravity for M2 should be greater. And it shows that in the diagram, and the tensions are equal, so their length should be equal. And on top of that, gravity is pointing down. The strings are attached from the top of the block, so tension's going up. I feel like the directions are pretty intuitive. So it says you get a point for drawing two vectors starting on the dots that point upward, have the same length, and are labeled as tension force. So to get your point for the tension here, you have to fit all those requirements. So the first requirement is starting on the dots that point upward. So if you get the direction wrong, you don't get the point. I said have the same length. So it says they have to be the same length. You have to make it pretty explicit that the two magnitudes are the same, or else you get it wrong. And you also have to label it as tension. A lot of people really neglect to label their free body diagram forces, which is kind of unfortunate, but it's because of time crunch, but just make sure you do that. And the next point says for drawing two vectors starting on the dots that point downward, where the vector for block 1 is smaller than the vector for block 2, and both are labeled as the gravitational force. So it says you need gravity pointing downwards on both of them. And it also says you need gravity for mass 1 being smaller. So again, if you don't draw that, you don't get the point. And then it says one earned point is deducted for drawing any extraneous vectors. So if you had anything else, the only thing I could see is like maybe like drawing a force of like air resistance, but they're not very well. They are moving, but that doesn't matter. But again, no extraneous vectors. Just do what the problem asks you to. It says one point is deduct for vector lengths that do not allow the system to accelerate in the proper direction. So what that's saying is if you drew m1g as greater than m2g, then it would accelerate in the wrong direction. So you do need that requirement there. The next part says derive the magnitude of the acceleration of block 2. Express your answer in terms of m1, m2, and g. So you need to write, well, the first thing you actually need to do is kind of define a positive direction for yourself. So we see m1a equals t minus m1g. So the problem with a lot of these problems is that it's really weird how to define a direction for it. So I'm going to look up an image on Google right now to show how people define it. So it is in chat. Copy image address. It's in chat in 3, 2. That's a long link. Hold on. There we go. So it is in chat right now. So if you look at it, you do see that one side is up and one side is down, and that's kind of how these problems always go. So you do need to define a direction in terms of like continuity of the rope, and it is curved around the pulley. So it says m1a equals t minus m1g. So if we go back on the m1 mass, they're defining tension as upward, whereas on the m2 they're defining m2g as upward, or positive rather. So you have m1a equals t minus m1g. So you have an equation, but you're trying to solve for both acceleration, but you don't have a tension. So you need a second equation to solve for tension, and that comes with the Newton's second law for block 2. You have m2a equals m2g minus t. That just comes from F equals ma. Both of them do. So you can eliminate t. What they did here is I actually have a really hard time following their math here. So what they did here was they use m1a equals t minus m1g to solve for t, and then they substituted that t back into the Newton's second law for block 2. And then from there, you have an expression with no t's in it, just masses, gravity, and acceleration. And you can solve for acceleration using some clever algebra, and you get that big expression there. This is an alternate solution. I don't really like this kind of solution where they use net force in the system, because this kind of solution only works if the pulleys are massless, and that's not going to be always the case in your future. It probably is for Physics 1, but it's kind of good to get into the habit of solving Newton's second law for both blocks, because that will always work, whereas this won't always work. So yeah, so basically what they did was they said for writing a difference showing that the net force acting on the system is the difference in masses times the acceleration of gravity. So basically what they did here is, if you look at the free body diagram, the tension is internal to the system, and they also cancel out. So the net force is the difference between the gravities. So that's what they did there. And then it also says for writing an equation that relates the net force to the sum of the masses and the acceleration of the system. So we have F net is equal to the mass of the system times acceleration. Because both those F nets are equal to one another, you can set them equal to each other and solve for A, which is actually mathematically easier for most people probably, but I recommend against it. So it says block 3 of mass M3 is added to the system as shown below. There is no friction between block 3 and the table, and it says indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as in the original 2-block system. Explain how you arrived at your answer. Yeah, actually, we can go over that towards the end. I'm going to use a whiteboard for that, but it's not in the slides. So it says the acceleration of the new system and of thus block 2 is smaller. So the reason why they say is because the mass of the system goes up, so the acceleration of the system must go down, which I think is pretty intuitive by F equals ma. And that's it, really. I really don't see the difference between the alternate solution and
They're pretty redundant, I agree.
Yeah, that's kind of the same thing. But
real quick for Jeffrey, do you want anything specific, like a period of a pendulum, period of a spring mass system, horizontal, vertical? Is there anything like specifically with SHM that you want?
Yeah, that'd be nice.
Yeah, we can sit on that. Maybe a vertical spring. Okay, cool.
Okay.
SHM springs.
Oh,
All
everyone
right.
wants springs. Yeah, the slides are
Yeah.
done, so that's good that you guys have questions.
Yeah, I'm glad you guys are interested in
Okay,
springs.
so I'm gonna go ahead and share my kind of whiteboard thing that I have here.
Awesome.
Okay.
Your bootleg software.
Yeah, my bootleg Photoshop. So,
Do you want me to find I have an old prep book I could try and pull a vertical
yeah,
spring out of.
that would be good because
All
I don't
right,
know what kind
I'll
of
look
SHM
for
questions you
it.
can ask for physics one.
Okay. I know that there's a huge emphasis on the period.
Yeah.
Okay, let me find one. Okay. All right, here's my Barron's book. Oh goodness, this is
All right.
quite an oldie. Okay.
I want to read it off on a bridge so we don't get copyright stricken.
Yeah. Okay. So there's rotational. All right. Let's move forward. I'm not seeing anything with vertical springs in here. Okay, so there's another question about key points to review over torque. Do you want me to talk about that and you try to find one with a vertical spring?
Yeah, that's a good idea.
Okay,
Especially since yours is
awesome.
very like talkable.
Okay, could you give us some key points to review over the unit for torque? Okay, awesome. I will grab that. For me, the biggest thing was the center of mass versus a single mass, like understanding what affects a system in torque. So I would really, really recommend looking over. I know we have a study guide on Fiveable for that, but there's also some really great College Board videos. I know Josh Beck, I believe, is one of the teachers, and he's phenomenal. But I can grab something out of torque real quick to give you guys some overviews because I still have my old torque notes. Okay, let's see. So inside of torque and rotational motion, that's going to be unit 7. So there's rotational kinematics. So you need to know angular displacement, angular velocity, angular acceleration, and kind of the difference between that and those linear quantities. If you want to write it mathematically, I believe it's AR, or the linear quantity multiplied by the radius. And then for torque, you need to know static rotation and Newton's second law. So I can expound upon that a little bit more. So there is a really great torque FRQ that I believe the advanced placement teachers went over, where it's your typical, like, there's a lever and then a block hits and you have to find, like, what is the torque of it and how does the system change in terms of energy, and also what applies a torque. Well, in torque itself, it has to be the product of the force multiplied by the distance between the force and the fulcrum. So it has to be perpendicular to the fulcrum, and that's a big difference between work and torque, because work is force parallel to displacement and torque is your perpendicular. So that's a big thing. There's also net torque and balancing questions. If you've ever seen those bridge problems where it's like one person stands on this end of the bridge and one person stands on the other, how are you going to balance this unknown mass with these other masses? Well, you do like torque in the clockwise direction is equal to torque in the counterclockwise direction, stuff like that. For torque, I would also review, there's a video I believe that the College Board did about that center of mass type of problem with torque. So definitely would go over that and understanding that, the problem we did, the 2019 problem, when a torque is applied to a system, like a net external torque, that'll change the angular momentum. But when just a force is applied, it won't necessarily change the angular momentum, like that plunger problem. Understanding what exactly applies a torque, I would really go over that. And also knowing what a net external torque does, because I would assume since all the FRQs are going to be written out, you're going to have to be able to explain what torque actually does. If you have any other questions about torque or what points you think you should go over, please let me know. Make sure you understand inertia. Also, kind of those parallels between linear and rotational quantities, that's a big deal. What else do we have? Could you guys over equilibrium problems. Yeah, we can do that after the spring. Okay, cool.
Okay.
So,
Yeah, I have something drawn out here.
all right, awesome. I'll let you take that over.
Okay, so vertical spring systems are basically exactly what it sounds like. You have a mass here attached to a spring with a given spring constant. A lot of people don't really know what this notation is with the dashed lines on the thing. That just means the wall is rigid, so it won't move. Or it does move a little bit, but it's negligible. So basically what you have here is you have this spring here, or this mass spring system right here, and it's in equilibrium. So it's not moving. And then you push it some distance delta y. So what is going to happen is once you push it that distance delta y, it's going to come up and then come down, and then come up and then come down. And assuming no air resistance, is going to do that infinitely. Again, which is why it doesn't actually do it infinitely, because there is air resistance in our world. we do live in an atmosphere. But for the first few iterations of the cycle, it does have sort of that infinite behavior. And we have this kind of big relation right here. So we have the period, which is how long it's going to take for this mass to go back to its original position, delta y. And then we have this frequency right here, which is how many times something completes that full cycle per second. We have an angular frequency right here, which I'll talk about in a bit. And then we have this right here, which is a relation between the mass and the spring constant, and the period. So these first three terms are kind of definitional. You can't really derive them or come up with them. That's just how the quantities are defined. This one right here is a little more obviously not definitional. However, deriving it requires some calculus that you guys aren't expected to know. So don't worry about it. Just take advantage of what some more mathematically experienced people have already come up with. So this omega term right here, this is what it's called. It's a funny little Greek letter called omega. It looks like a W. So what that's for is it's actually included in the equation of motion for something in simple harmonic motion. What we have is for simple harmonic motion, I'm going to call this, this x doesn't have to be a linear displacement. So we have x as a function of time is equal to a sine of omega t plus some phase shift phi. So what this graph looks like is exactly what you'd expect it to look like. It's just a wave. So this goes from negative a to a. This graph makes more sense if you take in pre-cal, this kind of concept in general. If you haven't, don't worry about it. It doesn't get too mathematically heavy for actually answering questions. So basically what this looks like is it looks like a wave that's much better than the one I'm drawing. It just oscillates back and forth between negative a and a. And the time it takes for it to return to its initial position, I should label my axes. This is x. Time. This length right here on the time axis is called the period. So, I mean, yeah, that's pretty much like the biggest extent you need to go with this kind of problems in the context of Physics 1, is knowing what terms mean what, knowing how to solve between these. This entire like orange relation, at least pieces of it, are on your equation sheet, which I think is really great. So, like, what often like a question they could ask is like, let's say you have just a typical mass on a spring, and then you add another mass. So this is mass m, this is mass m. So the period when it's m is 2 pi times square root m over k. But the period when you double that mass is 2 pi square root 2m over k. And then what you can do is you could actually bring out this root 2. So you have root 2 times 2 pi square root m over k. But by this equation up here, that is just also root 2t. So one thing they could ask you is, if you double the mass on a mass spring system, what happens to, or what's this ratio? So if you have like a final period and an initial period where the initial is mass m and the final is 2m, what's this ratio? And the answer is root 2 by this work right here. What they could ask you after that is, well, what about the angular frequencies afterwards? What we have here is we have period is inversely related to angular frequency, right? So you have t, you can multiply omega on the other side, so you have t omega is equal to 2 pi. Since this is a constant, if this goes up, this also has to go down, which by definition means they're inversely related. So this ratio is flipped as 1 over root 2. What else could I cover with this?
I do have another question if you think you've covered it all.
Do you think I've covered it all?
I have never heard a frequency problem in all my Physics 1 days, so I was pretty impressed.
Okay.
Okay.
Yeah, what else?
All right, do you want to, this is going to require like a new sheet of your software. And
I can do that.
It's a bridge problem that I mentioned. I'm very excited. Okay.
Cool. Let's hear it.
All right, so Bob is standing on a bridge. The bridge itself weighs 10,000 newtons. I love how you labeled it Bob. Okay.
So the bridge itself,
Mm-hmm.
how many?
10,000 newtons.
It's a lot of newtons.
Mm-hmm. Okay, so there's 2 pillars on either side, pillar A and pillar B. And the span between the pillars is 80 meters.
Okay.
Okay, Bob, whose mass is 100 kilograms. Let's get there.
Okay.
He is standing 20 meters from the center of the bridge toward pillar A.
Center of bridge toward pillar A. Okay, so or rather, center of the bridge toward pillar A. What do you mean?
So he's going to be 20 meters left of the center of mass.
Okay, so this distance, 20 meters. Cool.
Okay, so we want to find the force pillar A and B exert to prevent the bridge from rotating.
Oof.
Yes.
All
so
right.
we can go like a step by step, or do you just want to like attack it with Newton's second law?
We should definitely probably just attack it with Newton's second law.
Okay, cool. So identify all the sources of torque, I believe, is what we have to do first.
Okay, so what we have to do when we draw the three-bow diagram for the bridge is, I'm going to do a different color because there's a lot of red on this document right now. So this is the bridge. We'll name him Kevin.
Okay, perfect.
Kevin.
That'll be easy to differentiate.
So the forces. So we have, let's define a positive direction first. We'll say counterclockwise is the positive direction.
Awesome.
So this torque, the torque from pillar B, pillar B has a weight to it, so it's going to point down.
Mm-hmm.
So
which one do we want to make our fulcrum?
Wouldn't it rotate about its center?
No, in this problem with AP Physics 1, you're looking at like you have to make something a fulcrum. I know you're often like college physics,
you can make it your center though, right?
You could make it the center. Do we want to do that?
Let's do it.
All right, we can do the center of Kevin.
I'm a mad lad. We'll do it. Okay.
I don't mind.
So we'll have, there's a torque.
Oh, Jeffrey backed me up in the chat. Thank you, Jeffrey.
That's actually a good idea. Yeah, you're right, actually, because then we can eliminate one of them. Okay.
I think it's just going to be easier to do that.
Yeah, you're right. So we'll say this is the center.
Thank you, Jeffrey. Appreciate it.
Yeah, it's fine. I've been bullied the past.
Hey, you were asking for it.
All right, cool.
Your bootleg software.
Yeah, I don't want to hear it. Okay, so the force of gravity from B. So we're identifying the masses of the pillars.
So we're gonna identify the way that this is going through. So let's say pillar A is the fulcrum.
Yep.
and it provides no torque because the fulcrum, you need,
Yep.
remember the torque equation,
Yep.
radius or distance from the fulcrum, and we don't have that. So pillar A is good. It eliminates itself, like you mentioned earlier.
Yeah.
So pillar B is 80 meters from pillar A, which is our fulcrum, and pushes upward with a counterclockwise torque. That's how we're looking at it. It's keeping the bridge up. So for the bridge itself, we will look at the center of mass, which would be 40 meters from the fulcrum, and also provides a clockwise torque in relation to pillar B because of the force of gravity, like you mentioned. It's trying to pull down, while B is trying to keep that fulcrum upward.
Yeah.
Okay, so now that we have all of this, we know that pillar B, the torque that pillar B is exerting in the positive direction is equal to the torque of, well, also we have to include Bob's torque. I almost forgot about Bob.
Yeah.
Sorry. Bob is also pushing down with a negative torque in our scenario.
Okay.
So we have pillar B's torque is equal to the torque of Kevin plus the torque of Bob. So
I'm regretting naming the bridge now.
we have to oh gosh. Now we have to add the torque of Bob and the torque of the bridge to find the torque of pillar B.
Okay.
So do you want to calculate well, we have to find out what is the force of gravity on Bob so we can multiply that. I usually use 10 for acceleration due to gravity.
Yeah,
I don't know if you use 9.8 if you're fancy, but
no, it doesn't matter. So I don't have a calculator on me either.
okay, so Bob, I'm reading my notes here. Bob is going to be, okay, wait, let's look at this.
So
Okay,
Bob
the total weight.
A negative torque.
Mm-hmm.
Yeah.
And the bridge, Kevin's also exerting a negative torque. So we want to find the torque of each of them, add them together, and that's the torque of pillar B keeping it up. So I can save you some math here. Here we go. The bridge's torque is that's 400,000
Hold on, I need to
Newton meters.
I need to actually write all the variables first.
Okay,
So
cool. Let me know when you get there.
From B, so that's a positive quantity because it's in the positive direction.
Mm-hmm.
Minus the torque from Kevin minus the torque from Bob. Okay.
Oh, that's a good equilibrium statement. I didn't even think about making that.
Yeah.
Because we do know the bridge is in equilibrium. It's not rotating either side.
Yeah.
Okay, so once we have that, the torque of Bob is 20,000 Newton meters clockwise or in the negative direction.
We should probably explain that.
Okay, so what I did was first you find Bob's force. So Bob weighs 100 kilograms multiplied by 10 meters per second squared. The acceleration due to gravity is your force of gravity. So Bob's force of gravity is 1,000 newtons, and he is 20 meters away from pillar A, which is our fulcrum. So if you remember the torque formula, it's the force times the radius. So when you do that, you can find what Bob is doing in terms of torque. And the same for the bridge. We know the bridge is 40 meters away from the fulcrum, and it weighs 10,000 newtons. So it's going to be a whopping 400,000 Newton meters in our negative direction.
And then you said the torque for Bob was what?
And the torque for Bob is 20,000 Newton meters.
Okay. And first off, you said Bob was 20 meters from pillar A, right? Or fulcrum?
Yes.
Okay, so I need to fix this then.
Okay.
20 meters. That's wrong. Okay. And then what was the torque from fulcrum B?
The torque from fulcrum B, or from pillar B, the torque from pillar B, is, I didn't add all of them together. Oh my goodness. Okay.
I don't need to do that. Hold on.
Okay.
Yeah, that's literally just adding. I forgot how numbers work.
That's okay. I do that. I mean, physics 1 is really just ignoring numbers, but you still have to know how to work with them, so it's good practice.
Okay, so this is the first answer, right?
Yes. So the problem itself is asking for the force that pillar A and pillar B respectively exert to prevent the bridge from rotating. So now we have to find the force of B. We have the torque but we don't have the force. So then we want to find our force. So how far is B from A? That's what we want to know, because the torque formula gives us F times R. So in order to break it down, Jeffrey with another answer. Okay, so we want to divide 420,000 Newton meters divided by 80 on one side. You're getting this. To get the force of B, because that's what the problem is asking us. So let me know when you're ready for the number.
You know, I could have done this math in my head in like 4th grade.
Jeffrey did it again. Okay, I don't think we can keep going. I feel like Jeffrey can just take over. Perfect. Okay, cool. Okay, so now we have the force provided by pillar B. So what we want to do now is, if pillar B holds 5,250 newtons of the weight, how much does pillar A hold? Okay, so now we have to figure out, how are we going to find the force of pillar A now that we have the force of pillar B?
I think we just scrap torque in general, right?
I mean, at this point, yeah, because we just have to do the sum of the forces. But does anyone have an idea how we can approach it? If Jeffrey wants to hit us up with another one.
Yeah, if Jeffrey wants to work for Fiveable, he can.
Okay, so that's okay. What we're going to do now is the total weight of, we have to find pillar A. So we're going to use the sum of the forces, right?
Yes.
So, oh my gosh, I have to think this through.
There's a lot of forces here. So we have force A and B pointing up.
Yes. And then force of Bob and Kevin pointing down.
Yes. And then we have, yeah, both that.
So we have to do the sum of force pillar A and force pillar B equal to the sum of Kevin and Bob to find the force of pillar A.
Bob, F, Kevin.
Perfect. Okay. So our force of, we don't know the force of A, but we know the force of B is 5,250 newtons. And that's going to be equal to a, how big is that bridge? 10,000 Newton bridge plus Bob, which is 1,000 newtons. So it's just bridge force plus the man's force. Yes, Jeffrey, that is correct. You want to do the sum of the forces in the positive direction is equal to the sum of the forces in the negative direction, because our bridge is in equilibrium. That was a great observation. Okay. Are you ready for the pillar A? Or do you want to try the math?
I mean, it's just adding, right?
Yes. So it's 5,750 newtons. Now, you may ask yourself, why is it more than pillar B? Because Bob is exerting a force that is closer in radius to pillar A. So that's going to have to make, pillar A is going to have to push up more because Bob is there.
Yeah.
Okay. Awesome. Do we have any questions about the torque equilibrium problem? Yes, that is correct, Jeffrey. That was perfect math. Any more questions about this? I don't think so. Okay. Were there any previous questions that we missed?
Oh, someone said in class we had to find potential energy for spring and graph it. It was also voltage that was for finding energy, I think. I completely missed that question.
Oh no.
Potential energy for the spring and graph it. So that's a little bit vague because I'm not really sure what two quantities, so I'm going to go over the two that I can think of. So we can think of potential energy as U versus X.
Do you think they're referring to the conservation of energy, like, spring kinetic versus spring potential, like when it changes in those springs?
Yeah, I'll go over that too. So I'm going to graph position versus time, or rather potential energy versus time, potential energy versus position, and other stuff. So
Awesome.
we have u versus time, and then we'll say u versus velocity. So what we have is we have first u versus x. That's kind of the easiest one because that's on your formula sheet. So potential energy for a spring, 1/2 kx squared. That's just going to look like your basic parabola there. U versus time is a little harder, but we do have x as a function of time being a sine omega t plus some phase shifts that normally actually that phi ends up becoming 0. So you can plug this into here, and then you get u equals 1/2 k a squared times the sine omega t plus phi squared. You might see this as sine squared, but I'm just kind of ignoring that because a lot of people don't see that notation unless they've taken pre-cal, and I'm sure some of you haven't. So this graph also still looks like a sine graph, except it's always positive. So I'm going to refresh myself on what this graph looks like because I don't want to get it wrong and embarrass myself.
That's a good idea.
Okay, so what this graph ends up looking like is it ends up looking something that. Notice a difference between x of t versus u of t. What x of t would look like. So this is u of t. This would actually dip below the x or the t-axis every now and then, but this is because the quantity is squared. This potential energy will never be negative. And then u versus v. So basically what we have is we have conservation of energy, which says the final energy or the initial energy is equal to final energy, which is some constant. So we could take the initial point to be any point we want. So we could have 1/2, or rather, I'll start from step 1. Potential energy plus kinetic energy with some constant. If we want to graph potential energy versus velocity, we'd have ui plus 1/2 mvi squared is equal to some constant. So what we'd have is we have ui is equal to some constant minus 1/2 mvi squared. And what this graph will look like is it's some positive constant. Positive constant up here. So this is u as a function of v, and it's a downwards facing parabola. And what we noted before is that potential energy of the spring can never be negative, so it's not going to dip below the time axis.
Ooh, good question. Could there be questions with oscillations involving angles? I do believe that advanced placement went over one where it was like a spring, or no, it might have been a pendulum was pushed at an angle, but I don't think there's going to be anything mathematically based. You might just have to understand what's going to happen when it's pushed at an angle, like the force components. But I really don't see them putting a lot of math on this year's exam, unless you have anything with that one, Jacob.
Well, so oscillations in general, the math behind oscillations and like deriving the formula for a period and like small angle pendulum is math beyond algebra. So the furthest they can go is a pendulum. One thing I could see them asking is I'm gonna make a new one. They could ask like, let's say we have some pendulum, all its mass. I'll make fun of my thetas. With all its mass right here, like at the bottom, versus something that's like an actual like real pendulum, like a bar that has a uniform mass. Wow, that's an ugly bar. I cannot draw today.
It was, we knew what you meant. It was
Yeah, that's
close.
important. We'll call this theta 2 and theta 1 just because they're different. So let's say it has all the mass right here, and this is equal mass, but it's a bar. One thing I could see them asking is which one has the higher period. And what we actually have is we have the period is equal to 2 pi square root L over G. and people see, oh, it's mass independent, so the periods are going to be the same. That's actually not true. And the easiest way to conceptualize that is you can think of this bar right here as a sum of a bunch of tiny little pendulums, or pendulums like this. So like you could think of like the bar sort of looking like this. You have so that we could split this up into 3 balls of like infinite, or just infinite amount of density. Say this is 1/3 m, 1/3 m, 1/3 m. So this would be, the length would be L over 3, 2L over 3, and L. So what happens with this is, if we assume everything is rigid, the strings don't move with respect to the ball, so it all stays in one straight line. The period would end up being the sum of these. So it would be 2 pi square root. The m over here is 1 over 3m, and the length is L over 3. So 1/3 L plus 2 pi square root 1/3 m over 2/3 L plus 2 pi square root 1/3 m over L. And basically what happens is you have, all of these have a common term of 2 pi root m over 3. And then it becomes square root 3 over L plus square root 3 over 2L plus dot 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 with the other one. Or actually, I can just write that out. Just comes square root 1 over L. But you kind of have to take an average of them, sort of. Well, actually, that's beyond the point. But basically, this quantity right here ends up being smaller than this one. And you could keep up this pattern for an infinite amount of sort of subdivisions in the bar, and you get that this is actually smaller. This has a smaller period than that, despite the period formula being independent of mass. That's the most complicated question that I could see them asking you.
I was gonna say that was
So,
a really great visual for it, though.
yeah.
Jeffrey asked, how would y'all recommend studying the week before the AP exam? For me, when I was studying for AP Physics, I broke up the units into like 2 days I would devote to kinematics, 2 days I would devote to dynamics, leading up to the exam. I know we don't have that much time now, but there is a huge review, like I mentioned earlier, that Jacob and I are doing with Peter Apps, who is the Cram Physics 1 streamer. That's going to be like a 5-hour stream the day before. Definitely recommend doing that. This year's a bit different since it's open notes. I would really recommend preparing fact sheets, printing out study guides and stuff, but you don't want to have too much that you're sifting through in the exam. So my biggest advice would be, College Board released the 2020 like practice FRQs on the Physics 1 page. Go sit down at your desk, prepare it like you're going to have it ready exam day, have your notes to one side, have a timer out, and just time yourself and do it. And, self-score, I know there's a video explanation of it. I would really recommend doing practice exams. I think that's going to be your best help from now leading up to the exam. Do you have anything to add to that, Jacob?
Not really.
We have one more question. What would you say is the most important concept to study?
That's a loaded question.
That is a loaded question. My thing would be Unit 7. I've seen so many College Board videos on Unit 7. My feed has been disrupted with them. I would really recommend going over torque and rotational motion. But the kicker with that unit is it pretty much covers every other unit. So, I would really go over that one. That's just what I've been seeing the most of. And watch the Fiveable live streams to get the key concepts. And also there was a live stream with the NMSI AP readers that was really good. And I'm sure they had a lot of great tips. What is period 7? Oh, unit 7 is torque and rotational motion. All right. Do you have any last comments, Jacob?
No.
All right. Well, I think, are we at our time limit? Oh, is there a possibility of there being a rocket propulsion involving conservation of energy? Ooh, do you want to take that one?
I mean, I'm sure it's a possibility, but like when you get that specific, like you're not really like I think studying like the general idea of conservation of energy is a good thing, but I don't think going specific is like something as niche as a rocket propulsion is worth studying.
Yeah, that's probably a pretty specific topic. I don't know. They might have some insider knowledge into the exam. All right. Well, I'm pretty sure we are at our time slot for today.
Yeah,
So
we've
unless
been
there are
over our time
any,
slot for like 6.5 minutes.
yeah, unless there are any other questions, I think that we're gonna have to end the Q&A. But thank you guys so much for coming.
Yeah, thank you guys. Have a good night.
All right. Bye, guys.